These are the notes for AP Calculus on the topic of summary of volumes with calculator. So we've got three different types of volumes we've gone over thus far using calculus. So let's compare and contrast them so that you understand the difference between them and don't get them mixed up. So the first two look very similar because both on the disk method and the shell method, both of them are rotated or revolved around an axis of revolution. And both of them use a vertical rectangle with dx. Let's draw that here so you can see the difference. And then one of my former students came up with a little mnemonic device to make it easier to tell which method to use. So if your axis of revolution is perpendicular to the rectangle, like this, and you can remember it's perpendicular, and then that's the disk method. And with the disk method, remember we have pi on the outside, and then we need the outer radius, R1, squared. So the outer radius goes from the axis of revolution to the far end of the rectangle. And if there's any gap between your region enclosed and your axis of revolution, like there is here, then you'll also need an R2, and you'll have to subtract the inner radius squared, which is from the axis of revolution to the close end of the rectangle. And for both of these, remember, since they're vertical distance, you do the top minus the bottom to find their expressions. But for the shell method, instead of perpendicular, if your axis of revolution is parallel, or you can remember para-shell, to the axis of revolution in the rectangle. If those are parallel, para-shell, you can remember it's going to be the shell method. And with the shell method, to help you visualize it, it's called a shell because it's a cylindrical shell. And the two things you need are the radius and the height. And the radius on the shell method we call P of x, goes from the axis of revolution to the rectangle. And the height we usually refer to as h of x, is the top minus the bottom of the rectangle. That's the height of the cylinder. So with the shell method, instead of a pi on the outside, we have 2 pi. And then we just take P of x, which would do the right minus the left. And wherever your rectangle is x. And h of x would be the top minus the bottom of the rectangle. And those you just multiply together. And on both of these, since everything is in terms of x, one thing they have in common is the a and b values for both of these. The lower and upper limits, you're always using the x coordinates, where the region begins and ends from the left, moving from left to right. All right, so let's see how this works with this example problem. We're going to do all these with the graphing calculator today, so I'll show you on both the TI-84 and the TI-Nspire. Let's start with the 84. Let's enter these in. So hit y equals, and we've got 2 sine of x divided by 2, close parentheses, plus 4. And then for y2, we've got 0.2, or you can just put 0.2, second e. Again, if you have a newer one, it moves it up to be the exponent. On this one, you just have to put in parentheses, x, close parentheses, and then plus 3. Make sure that plus 3 is not up in the exponent. And then before we graph it, let's change our window size here. So on your homework, you'll just have to look at the scale if it's given to you, which in this case it is. So let's go from -7 to 7. Use the negative in parentheses out in front on the x minimum and x maximum. And for the y minimax, let's go -1. That way we can see the x-axis all the way up to 7. And remember, it's going to graph in the order we type them in. So there's the graph of f of x, and then there's the graph of g of x. So let's label those on our graph now. So this one was f of x, and this one was g of x. And remember in our calculator, this was y2, and f of x was y1. All right, so now let's look at the TI Nspire and see how we put those in there. So new document, add graphs, and then f of x E2, and then hit the trig button for sine. If you want to write as a fraction, you can hit the fraction button here. Oops, go back to tab here. 2 sine, fraction button right here, x over 2, or you could put x divided by 2 either way, and then plus 4. Hit the down arrow, and then g of x, or f2, is 0.2x, sorry, 0.2e to the x. And then just hit the right arrow to get out of the exponent, and then plus 3. You can see it here, but let's change our window size the same as the TI-84. So menu, window zoom, window settings. Again, let's go -7 to 7, or x-min and x-max, and -1 to 7 for the y-min and y-max, just so we can zoom in out a little more. There we go. All right, now let's look at the first one. It says find the volume of the solid gel in region S. Make sure you look at what region it is. Is rotated about the line y = 1. Okay, so when it's rotated, it's either going to be a disk or a shell. So let's see how we can figure out which one it is. So first, draw your vertical rectangle in region S, somewhere in here. Notice it always stays between the same two curves there, with dx. And then let's draw y = 1 as a dotted line. So we don't confuse the region enclosed. So y = 1 gives us this horizontal line right here. Oops. So put a little circular arrow, we're revolving around that. So notice the rectangle and the axis of revolution are perpendicular, so it's the disk method. And our R1 would go from the axis of revolution to the far end of the rectangle. That's the outer radius when it revolves around here. So let's write that down first. R1 equals, and since we want a vertical distance, remember you go the top minus the bottom. And the one on the top you can see is g of x minus the one on the bottom is 1. Forgot to label it here, but this is y = 1. So it'd be g of x minus 1. And in this case, there is an R2 because there's a gap between our axis and our region enclosed. R2 goes from the axis of revolution to the close end of the rectangle. That's the radius of the hole. So for R2, again, looking at the top minus the bottom, the one on the top of R2 is f of x minus the one on the bottom is 1. So it'll be f of x minus 1. And again, unless it's about the x-axis, you're going to see this similarity between R1 and R2 on the disk method. So now let's finish setting it up. Our integral. We've got pi on the outside. But then notice we need to know where the region starts and stops. So let's go ahead and start finding our points of intersection. So for S, I'll call this one. We might need the y coordinates later, so I'm going to find them both right now just in case. So I'll call the x coordinate A, the y coordinate B. Let's go ahead and find that first. So second calc intersect. First curve, there's only two curves there. Enter, second curve, enter. I'm going to guess this one's over at -4. So I'll just type in -4 for the guess. And it's -5.237 for the x and 3.001 for the y. So let's write those both down on paper, then we'll store them in our calculator. -5.237. And b is equal to 3.001. All right, so let's go ahead and store those now. So go second quit, and then for the x coordinate, you can just hit store alpha a. But for the y coordinate, remember you have to access that by going alpha and then y, which is on the number 1, and then store alpha b. All right, now let's find our other point of intersection here. Call this one CD for the x coordinate and y coordinate. Let's find those and store them in our calculator. So second calc, number 5 intersect. Again, first curve, hit enter, second curve, enter. I'm going to guess this one's at -1. Just type in -1 for my guess. And it's negative 0.960 for C. You got it. And for the y coordinate, we got 3.077 for our D. Again, let's store this in our calculator. So second quit, store alpha C and alpha Y, the y coordinate, store alpha D. All right, and now let's do the same thing on the Inspire. So for the Inspire, go menu, analyze graph, intersection, and lower bound just click to the left, upper bound to the right, and it gives you both coordinates. So highlight the x coordinate, var, store, and just put an A and enter. And then click on the y coordinate, var, store, var, and B, enter. And then if they get in the way, you can kind of move them around here. And then we go menu, analyze graph, intersection. This time lower bound to the left of this one, upper bound to the right. There it is. So click on the x coordinate, var, store as C. And click on the y coordinate, var, store as D. All right, so now we're all set. So now in this case, since it's in terms of x, we want to use the x coordinates. So moving from left to right, the region starts at an x coordinate of A, stops at an x coordinate of C. So from A to C on our lower and upper limits. And then we just have the R1 squared minus R2 squared. So R1 is g of x minus 1 squared minus R2 is f of x minus 1 squared. And then just don't forget the whole thing, big parentheses, times dx. All right, so let's go ahead and enter this in our calculator. Start with 84. So pi first, second pi, and then math number 9. And again, those of you guys who have the newer 84s, it will pop up just like this. You can put in alpha A and alpha C here. And then once you get the cursor here, and that's what I need here, we need to open parentheses. And remember, g of x is in our calculator is y2. So vars, y variables, number 1 function, y2, minus 1, close parentheses squared, minus, and then we need another open parentheses. And f of x in our calculator is y1. So vars, y variables, number 1 function, minus 1, close parentheses squared. And then the newer ones, you can just put the x right here, and you're all set to hit enter. On older ones like mine, comma x, and then comma the lower limit first, alpha A, comma the upper limit, alpha C. Close parentheses. And we get 28.510. That's our volume. And then if you want, you can put units cubed to remind yourself it's volume, but you don't have to. All right, and now let's do the same thing on the Inspire. So on the Inspire, doc, insert calculator, and pi is on the pi button right here. And then integral is right next to the 9, use the definite integral. And then we go from A to C, and then open parentheses. And G of x was our f2, var f2 of x, you have to put it, and then minus 1, and then we need squared, and then minus another open parentheses. F of x was y1, f1, f1 of x minus 1 squared, and then all times dx. Same thing. All right, now let's take a look at part B. Now it says we want to find the volume of the solid generated with region T. So we're looking at a different region here. It is rotated about the line x equals 4. So notice the wording is very similar on these, but let's look at region T. Let's draw a vertical rectangle in there. Again, with disk and shell, you always use a vertical rectangle when it's rotated. Either method. I'll just draw it about right in here. Draw it anywhere in there. And then dx. And this time we're rotating, I'll draw this as a dotted line, about x equals 4. Which is a vertical line right here. So now look, the axis of revolution and a rectangle, they're parallel, so think para-shell. I can remember it's the shell method. So here, to help you visualize, you don't have to draw this, but it helps you visualize the cylindrical shell that we're finding the radius and height of. The P of x goes from the axis of revolution to the rectangle. There's the radius of their cylinder, and h of x is the top minus the bottom of the rectangle. That's the two things we need. So this time we're using the shell method. So let's start with P of x, the radius. Well, since it's a horizontal distance here, so the one on the right goes first because that has a bigger x coordinate. So the one on the right is 4 minus the one on the left. Wherever your rectangle is, because you could draw it anywhere, it just represents x, the x coordinate. So it'd be 4 minus x. And then h of x would just be the top minus the bottom of the rectangle. In this case, for region T, the one on the top is f of x minus the one on the bottom is g of x. So it'd be f of x minus g of x. And then when we set up our integral, notice we can see where it starts at C, but we don't know where it stops here. So I'm going to call this point right here capital E, capital F for x and y coordinates. So let's find them, write them down, and store them in our calculator. So let's start with 84. So second calc, intersect, first curve enter, second curve enter. I'm going to guess they intersect around 3, so type in 3, enter. And it's 2.619, so that's our E value. The x coordinate, and then notice the y coordinate was 5.949. All right, so let's store those now. So I can quit, store alpha E, enter, and then alpha Y, or alpha F. There we go. And then on the Inspire, again, just go click back on the 1.1 for the graphs, menu, analyze graph intersection, lower bound to the left of it, upper bound, click to the right of it. There's our E, so var store as E, and y coordinate var store as F. All right, so now we're all set. So now, since it's the shell method, instead of pi, we'll have 2 pi. Again, everything's in terms of x. We use the x coordinates. So moving from left to right, this one has an x coordinate of C. It starts there. This one has an x coordinate of E, so from C to E. And then P of x and H of x just get multiplied together. So it'd be 4 minus x times f of x minus g of x. is our h of x. Dx. All right, so let's go put that in our calculator here. So we have 2 pi on the outside. And then math number 9. And again, for the newer ones, you can put alpha c and alpha e right now. For the older ones, parentheses. And right here, 4 minus x. Close parentheses, and then open parentheses. Then f of x was y1, so vars y variables. y1 minus g of x is y2, and then close parentheses on the older ones, comma x, comma lower limit alpha c, comma upper limit alpha e. And we get 63.000 units cubed. And then on the Inspire, we can go back here, put 2 pi on the outside, and then the integral next to 9 from c to e. Use the arrows or the tab. And then we get 4 minus x, so open parentheses, 4 minus x. Sometimes after this you have to put it times, but I think on this one we don't have to, especially when the radius is just x. And then f of x was f1 of x, minus g of x was f2 of x, times dx. We get the same thing. All right, so that's how you can tell the difference between the disk and shell. If it's perpendicular to the axis of revolution, the rectangle, it's the disk method. If it's the axis of revolution is parallel, parashell to the axis of revolution, the rectangle, then it's the shell method. But these other ones are worded differently, okay? Because these we're not rotating about anything. We just have region S, we're back to, is the base of a solid. For the solid, each cross-section perpendicular to the x-axis. So that's telling you it's a vertical rectangle right there. So everything's going to be in terms of x. And we've already drawn that one for region S. So we can use the same one we've already drawn. And now this is going to be our base. Call it B sub 1. Since we'll have a different base on problem part D. So our base, B sub 1, would be the top minus the bottom, which in this case is g of x minus f of x. And then remember, we derived these before, the shape we have, the cross-section of the isosceles right triangle with a leg along the base. Remember the area formula we got for that was 1/2 b squared. So when we set up our integral, it'll be 1/2 on the outside. And since everything's in terms of x, we'd use the x coordinates again for region S from A to C. And then it's just our base squared. So g of x minus f of x squared times dx. So now we can just put this in our calculators. Start with the 84. So nothing on the outside, I'm sorry, 1/2 on the outside on this one. So you can put 1/2 or 0.5. And math number 9. And then alpha A and alpha C if you have a new one. And then open parentheses. G of x is y2, so vars y variables y2 minus f of x is y1. Vars y variables y1, and then close parentheses squared. And then an old one, comma x, lower limit alpha A, upper limit alpha C. And we get 1.124. And if you want to remind yourself its volume, it'd be units cubed. And then Inspire real quick. Just have 1/2 on the outside. Integral from A to C. And it was g of x minus f of x squared. So open parentheses, g of x was f2, x minus f of x was f1 of x. The whole thing is squared times dx. Get the same thing. All right, the last part, now we're back to region T again. But this time it says each cross-section perpendicular to the y-axis. So the y-axis goes like this, perpendicular to that, so that's what tells you it's a horizontal rectangle with dy. And that means we need to get the whole integral in terms of y. So let's draw that in there for region T. So now we have to solve these equations for x in terms of y. So let's start out with a sine one. So instead of f of x, we could just write y equals 2 sine of x over 2 plus 4. So to solve this one for x, we first have to isolate the sign. So subtract the 4 first. So y minus 4 equals 2 times the sine of x over 2. And then you would divide by 2. The sign by itself. Now here you can leave it like this, but then you'll have an extra parentheses in your calculator you have to type in. So in this case, since 4 is divisible by 2 evenly, it's probably easier to split y divided by 2 minus 4 divided by 2 is 2. And then we've got the sign by itself. And then to get rid of the sign, to help us get the x by itself, the inverse of sine is arc sine. So you would take the arc sine of both sides. Equals x over 2. And last step to solve for x, you would just multiply by 2. So we get x equals 2 times arc sine of y over 2 minus 2. Okay, and let's do the same thing for the other one. So the other one, we've got g of x, which is like y, equals 0.2 e to the x plus 3. So here you don't isolate the e to the x first. Help us solve for x, so subtract the 3 first. So y minus 3. And to make our next step a little easier, instead of 0.2, I'm just going to write as a fraction. That's 2/10, which reduces to 1/5. And then you can just multiply both sides by 5. So that's going to give you 5y minus 15. 5's cancel out there, equals e to the x. And then we can switch to log form to get the x out of the exponent. So it'll be log base e. Remember the log equals the exponent, so it's going to equal x of 5y minus 15 equals x. The exponent, and then you can rewrite log using ln. So x would equal natural log of 5y minus 15. All right, so then to get base 2, our base for this one, and you want a horizontal distance, just like we did for p of x here, be the right minus the left. So the one on the right, notice, comes from g of x. So that's the second one we found. So our base 2 would equal natural log of 5y minus 15 minus the one on the left is our f of x1, so that'd be 2 arc sine So I'm running over there of y over 2 minus 2. And so then we can set up our integral here. This time we've got a semicircle. So remember, we figured out the area of a semicircle on these cross sections was pi over 8b squared. So we can have pi over 8 on the outside. This time, though, the integral, since everything's in terms of y, we have to use the y coordinates. So we go from the bottom to the top of region T. So notice it starts at a y coordinate of D and stops at a y coordinate of F. So it would be from D to F. And then we just have our base here squared. So parentheses, natural log of 5y minus 15 minus 2 arc sine of y over 2 minus 2. And then the whole thing squared times dy. So on the Inspire, you can type it in just like this, and you can actually use y. But on the 84, it doesn't let you type in y. You have to put an x everywhere there's a y. So we'll put pi over 8 first, and then math 9, and then natural log. Well, first we need to open parentheses so we can square this whole thing. Natural log 5y minus 15, close parentheses, and then minus 2. And remember the calculator arc sine, looks like second sign with a negative 1, and then we'd have x divided by 2 instead of y divided by 2, minus 2, close parentheses on the arc sine, and then close parentheses so we can square the whole thing. And then our variables x, lower limit alpha d, upper limit alpha f. Oops, I put 57 instead of 5y. Whoops. Let's change that. Let's go second entry. Yeah, I meant to put an x there. I actually put 57. Let's try that again. Yep, so we got 1.806 units cubed. And that concludes the notes for AP Calculus on the topic of summary volumes with the graphing calculator.